Welcome to Classes with Atish. In this episode, we will continue with our chapter on work and energy. If you have not reviewed part 1 of this chapter, I'll put a link up on the screen so you can go ahead and check that out. It is recommended that you go over part 1 first so you can follow along what we discuss in this episode. So with that, let's get started. We will begin with the concept of conservative and non-conservative forces. Conservative force is a force where work done by that force on a body only depends on the initial and final position, and it is independent of the path. So let's say a body goes from point A to point B along path 1. Let's say it also takes a direct straight line path from A to B, or it could take another path from A to B. So let's say this is path 3, is path 2 and path 1. Okay, so a conservative force is one where the work done by the conservative force is independent of the path. So work done in path 1 is same as work done in path 2 is same as work done in path 3. Okay? Now a non-conservative force would be, it depends, non-conservative force, let's say. A non-conservative force would be a force where work done in path 1 is different from path 2, is different from path 3. So let me write that out for you. Only depends on initial and final position work done by a conservative force only depends on initial and final position, and second is independent of the path. Okay, and work done by a non-conservative force is dependent on the path. Okay, so what could be examples of conservative force? Examples of conservative force would be gravitation force, spring force, like when a spring is elongated or compressed, then the spring exerts a force, that's called spring force. We'll talk more about that. Electrostatic force. So these are examples of conservative forces. Okay, examples of non-conservative force would be friction force. There are many more non-conservative forces, but we'll discuss those as we go along. So let's show you how a gravitation force, for example, is a conservative force and how a friction force is a non-conservative force. Okay, so let's just show how gravity force is a conservative force. So we said a conservative force is one where work done by that force depends only on the initial and final position and is independent of the path between A and B, the initial and final position. Okay, so let's take an example. There is an inclined plane and there is a mass m here. Some forces pull this up from point A to B, okay, along the inclined plane. Now there are multiple forces plying here, so the force that pulled it up, but then there is normal reaction, there is force of gravity, there is friction. So there are multiple different forces, but we are only concerned with work done by gravity. Okay. Okay. So let's say path 1 is A to B via that inclined plane, and path 2 is A to O, and then from O to B. Okay. So let's calculate work done by gravity in path 1. So based on definition of work done by gravity, or work done is, it is the dot product of force times displacement. Okay. Now if I look at quickly the free body diagram of the mass m in this inclined plane, mg is the gravity force, and suppose this is the inclined plane. Let's say this angle is theta. Okay, so this angle is theta. Okay, so the component of mg along the inclined plane will be mg sine theta, and along this will be mg cos theta. Now work done by gravity, we have to take the component of force in the direction of displacement. Now displacement is happening in this direction, and it's equal to AB. So we can write this as mg sine theta into AB, okay, the length AB. Now we have to put a minus sign because the displacement is from A to B, but the component of gravity along that is in the opposite direction. So minus mg sine theta AB. Now sine theta we can write as OB divided by AB times AB. So this is minus mg OB. Now if OB is, let's say this is height h, then we can simply write minus mg h. Okay. Now let's consider the work done by gravity in path 2. Path 2 is what? We are taking the mass from A to O and then from O to B. Okay. So we can say work done by gravity from A to O plus work done by gravity from O to B. Now in this case, the gravity force is this way, but displacement from A to O is this way. So that makes a 90 degree. So cos 90, because it is Fs cos theta, cos 90 is 0, so this is 0. And in the other part, when the mass is moved from O to B, the displacement is in this direction, O to B. So this is, again we have to write minus mg times OB, and OB is height h, so minus mgh. So you can see work done by gravity, whether we go through path 1 or path 2, is the same. So it's independent of the path. So work done path 1 is equal to work done in path 2. So gravity force, therefore, is a conservative force. Okay. Now let's look at friction force and show you some way how it is a non-conservative force. Let's say we have a table. Okay, this is a rough table, which means there is some friction, and we have a body at point A, and we take the body to point B like this. Okay, and from point B we take it here like this, C. Okay, this distance is L, this distance is L. Okay, and then we do another experiment. We take the body from point A to point C directly. Okay, now this distance is root 2L. Okay, because this is a 90-degree. Okay, now if friction force is a conservative force, then work done in taking the body from, by friction force in taking the body from A to B and B to C must be equal to work done by the friction force from taking the body from A to C. Correct? So all along the surface of the table, if I look at the body, this is its free body diagram, mg, normal reaction, and whichever direction the movement is, friction force is in the opposite direction. Let's suppose we have a force, constant force F, that is being used to move the body along from point A to B to C, or from point A to C. Okay, so this is the free body diagram. Now friction force is same from anywhere you move along the table surface, and which is equals to mu into n, which is mu mg. Okay, now let's consider path 1 is AB, or we can write A to B and B to C, and path 2 is A to C. Okay, so let's do work done in path 1 is work done in moving from A to B plus work done in moving from B to C. So friction force is always opposite to the direction of displacement. So minus mu mg into L, and again from B to C is minus mu mg into L, or it is minus 2 mu mg L. Let's now see work done in path 2. So work done in path 2 will be minus mu mg times path AC, which is root 2L. So this is equals to minus root 2 mu mg. So you can see work done in path 1 is not equal to work done in path 2. There is lesser work done by friction force from moving it from A to C. Now we have been talking about conservative and non-conservative forces, but why is this important? It is important to study conservative force because it leads to the definition of potential energy. One more thing about conservative force. So we said the work done by a conservative force, let's denote that by WC, is dependent on the initial and final positions only. Let's say initial position is A, final position is B. Okay, what if a body displaces from along some path to B, and then it again finds its way back to A, so that this is a closed path. Okay. What is the work done by a conservative force in a closed path? So let's call this a closed path. So in a closed path, the initial and final position is the same. So work done by a conservative force in a closed path, is 0. Okay. By the same definition of conservative force, we can also infer that work done by a non-conservative force in a closed path is not always equal to 0. Okay. Or we can just say it's not equal to 0. Okay. So how can we use this information to make our lives easier? Let's say there is a rough, very irregular hill, okay, and a mass starting from here, it is taken along this rough hill and finally it comes to the top of the hill. Okay. Now if I have to find out work done by gravity force on this mass in the journey from here all the way to here, we don't need to do any complicated mathematics to find out what is the total work done along that path. Because work done by a conservative force is independent of path, we can always choose the shortest path, which is the straight line from here. Okay, so that is one. Second, if let's say there is a projectile, okay, and this ball is projected like this, it obviously follows a path like this and comes to rest at the same height at where it was launched from. Okay. In this case, work done by gravity is again 0. Why? Because gravity acts downward, mg. So there is no work done by gravity for this horizontal displacement because that is at 90 degree. The only work done by gravity is in the vertical displacement. Since vertical displacement is 0, it can be considered a closed path. So work done by gravity is 0. It's very easy to calculate. Okay. Now, let's define what is potential energy. Now, why did we learn about conservative and non-conservative forces? I think it was to be able to define potential energy. Potential energy is only defined for conservative forces. Potential energy has no meaning for non-conservative forces. Okay? So, potential energy, another thing, we can only define a change in potential energy. Absolute potential energy cannot be defined. We can assume potential energy at ground to be 0, and then we somehow talk about absolute potential energy, but then again there is no concept about absolute potential energy. It is only change in potential energy that is defined. Now change in potential energy is, so change in potential energy due to a conservative force, let's be very specific, okay, is equal to negative of work done by the conservative force. Okay, very important. So the change in potential energy due to some conservative force is negative of work done by the conservative force. So for example, let's see what is the change in potential energy due to gravity force, and gravity force is a conservative force. Let's say a body was on the ground and it is pulled up to a height h from the ground. Okay, so there is some work being done against gravity, correct? So the work done is negative. We are doing some work against gravity. Whenever work is done against a conservative force, that work is stored as potential energy. Okay, so what is the work done by gravity in this case? mg is downward direction and h, the displacement is in the positive direction. So work done by gravity is minus mgh, and we are defining change in potential energy due to gravity as minus of work done by the conservative force, which is in this case gravity. So this turns out to be mgh. Okay, now change in potential energy can be set as uf minus ui, potential energy final minus potential energy initial, equals mgh. Okay, now if we assume the potential energy, initial potential energy at ground due to gravity to be 0, we then can say potential energy at a height h is mgh. Okay, this is assumed. The formal definition is only for the change in potential energy, which is equal to negative of work done by a conservative force. Now, if we look at a small change in potential energy is due to a small work done by a conservative force. So du equals minus dwc, and small work done we can represent that as force times displacement. Okay, and we integrate that, let's say from S1 to S2. Be careful to ensure that this force is a conservative force. Okay, so this is only applicable for conservative forces, don't forget that. Okay, so if change in potential energy is applicable to conservative forces, we know few conservative forces. Gravity is one, or gravitational force. Then we have spring force. And we have electrostatic force. So all of these are conservative forces. So there must be some potential energy associated with each of these conservative forces. So the gravitational potential energy U is minus g m1 m2 by r, where if you remember, gravity force is defined for between two masses m1 and m2 separated by a distance r. The gravity force is g m1 m2 by r square. The gravitational potential energy is minus g m1 m2 by r. We will do this derivation when we talk in more detail about gravitation, but we'll go over that later. Okay. Spring potential energy or spring force potential energy is half kx square. Okay, where like if there is a spring, the spring constant is k, it is elongated by a distance x or compressed by a distance x, doesn't matter. The potential energy due to a spring is always positive because x, whether it's positive or negative, it's squared, half kx squared. We'll do this derivation shortly. And electrostatic potential energy or electric potential energy, U k q1 q2 by r, very similar to gravitational potential energy. Here k is the Coulomb constant, q1 q2 are the charges with the respective signs, and r is the distance between the charges. Okay, so one thing to understand here is the gravitational potential energy and electrostatic potential energy can be negative, but spring potential energy is always positive. These can be negative. Okay, we'll do this derivation shortly, but it's good to remember this. Additionally, I will just put down q1 q2 separated by r. The electrostatic force is 1 by 4 pi epsilon 0 q1 q2 by r square, very similar to gravitational force. Let us now try to derive the potential energy for gravitation and spring force and see how we can arrive at those expressions. Okay. Now gravitation force, we have two expressions for that. One is gravity near earth conditions. We write Fg as mass times g, where g is a constant near the earth, but there is some approximation that goes into here, so that's how we arrive at this expression. But the real gravity force, let's denote that by capital G, is gravitation constant m1 m2 by r square, where m1 and m2 are 2 point masses, okay, and they are separated by a distance r, and capital G is the gravitation constant. Now this is an approximation of that because what we assume is one of the masses is earth. Okay, so let's say this is mass earth. Okay, and there is a small body, small m, near the earth's surface. So essentially what happens, the gravitation force becomes capital G, mass of earth times the small body, divided by r squared. There is some radius of the small body, but that is very negligible in comparison to the radius of the earth, which is r. So we can just replace that by g mass of earth times m by r square. Now these are all constants, and that is how we replace that constant with this small g, and we come to that approximation. Force of gravity near the earth is mg. Okay, but now we will look at this expression for the gravitational force. So let's say there are two bodies, m1 and m2. Okay, now this m2 is initially at infinity and we are slowly bringing it because of the force of attraction. The body m2 is coming from infinity. The force of gravity is an attractive force, so m1 attracts m2 and m2 attracts m1. Let's say this force is represented by Fg, and let's say m2 initially was at infinity, and because of this force it is slowly coming to this position. Okay, and this position, let's say it's an arbitrary position r from m1. Okay, let's say m2 was at some distance x from m1. At this point it is experiencing a gravitational pull from m1, which is Fg, and Fg is g m1 m2 by x square. Okay, in this direction. Let's say the body is moved from this position by a distance dx away from m1. So there is some potential energy that the body gains because of the gravitational pull. It's similar to the situation where a mass was at a height h1 from the ground, and we're pulling the mass from height h1 to height h2. Okay, so we are doing some work against gravity. Same way here we are pulling the body by distance dx from this point, and there is some work that is being done against the gravitational pull, and that is stored as potential energy. Okay, so in this case the force Fg as a function of x is g m1 m2 by x square. Now the small work done by gravity when the body is moved by the distance dx is equals to Fg dx. Now let's be mindful about the signage. Fg is this side, dx is that side, so the work done is negative. So this, okay, one other thing. Now change in potential energy due to gravity is defined as negative of work done by the conservative force, which is gravity. So change in potential energy is equals to Fg dx. Okay, or we can further write this as g m1 m2 x square dx. Now if we integrate both sides, let's say we integrate this and we are integrating the right side, g m1 m2 by x square dx. Now what's the range of x? We are bringing x ranging from infinity to r. So infinity to r. Let's say the potential energy at infinity is u infinity and at r is ur. Okay, so this becomes g m1 m2, it's a constant. This is dx by x square, integral of that is minus 1 by x, and the limits are infinity to r. So we can further write this as minus g m1 m2 1 by r minus 1 by infinity, which is 0. So this is equals to minus g m1 m2 by r. Now let's look at the left side. If you integrate this, this becomes, we can rewrite as ur minus u infinity is equals to minus g m1 m2 by r. Now if we assume potential at infinity due to gravity is 0, then we get the expression for potential at a distance r is minus g m1 m2 by r. So when potential energy due to gravity is expressed as negative, it means m2 is bounded to m1. Okay, so that's the meaning of negative potential energy, and gravitational potential energy will always be negative. Okay, now let's look at spring force. So what is the spring force? Let's say we have a spring. Okay, and so this is the natural length of the spring. x0. What is natural length? Natural length means it is neither elongated nor compressed. Okay. Now, if I elongate this spring to some elongation x1, okay, elongate the spring from its natural length to some length x1, the spring force, the spring will pull it in the opposite direction based on the spring constant k by the distance that it is elongated. So minus kx1. So that is the spring force. Okay. Similarly, if we compress it by x1, the spring force will be pushing with kx1. Okay. Now let's say we elongate it to x1 and then we elongate it to x2. So we can say that originally it was at x1 and then we further elongate it to x2. Okay. So the spring stores potential energy when we do some work to elongate it by some distance. String stores potential energy when work is done to elongate or compress it by some distance x. We can also interpret this as whenever energy is imparted to a system, it is stored as potential energy. Now let's find out what's the work done then. So small amount of work done by the spring force when we elongate it by distance dx is this, or we can write this as minus kx dx. Okay. Now potential energy is defined as negative of work done by a conservative force. Okay, or let's just denote it as Ws and Us. So we know it is spring force. So this is equals to kx dx. Now if we integrate both sides, we are elongating it from x1 to x2. Let's say the potential energy at x1 is 1, potential energy at x2 is 2. This becomes kx square by 2, and the limits is from x1 to x2. So this becomes half k x2 square minus x1 square, and we can write this set as u2 minus u1, so which is the change in potential energy, is equals to half k x2 square minus x1 square. Now if x1 was the natural length, x0 let's say, and we denote x as the elongation, so x2 minus x0, then we can rewrite this as u x at any x minus u0 equals, we can write this as half k x square. Now if we assume at natural length of the spring at x0 u0 is 0, then you get the expression ux equals half k x square. Now notice here, since x is squared, whether you are elongating a spring or you are compressing a spring, potential energy of a spring is always positive. This is always positive. Okay? Whereas remember that gravitational potential energy can be negative. Okay, so we have been talking about potential energy, and change in potential energy of any conservative field is defined as negative of the work done by the conservative force. Okay, and how do we find if a force is conservative or not? So a force is conservative if the work done by the force in moving a point from A to B does not depend on the path, and it only depends on the initial and final positions, correct? Now suppose a force in the vector form is given as fx I cap plus fy j cap plus fz k cap. How do we know if this force is conservative or not? This F is conservative if and only if the partial differential del fx del y is equal to del fy del x and del fx del z is equal to del fz del x and del fy del z is equals to del fz del y. These are AND conditions, so all of these must be satisfied. So only if this is satisfied, force F is a conservative force. Only if force is a conservative force, potential energy is defined for that conservative force. Okay? Let's talk about a very well-known law of conservation of energy. Most of us have read about law of conservation of energy in our lower classes. We typically said mechanical energy is conserved, so kinetic energy plus potential energy is conserved, so constant, so we say energy is conserved. But this is an only approximation for a very specific scenario. This is not the true story. Let's talk about the true story, what's happening. We had talked about work energy theorem. What does the work energy theorem say? Work energy theorem says work done by all forces is equal to the change in kinetic energy of the body. Now remember, this is work done by all forces. So what does all forces comprise of? This really is all forces, all internal forces, all external forces, whether it's conservative force, non-conservative force, if we are dealing with non-inertial frames of reference, we also have to consider pseudo forces. Okay. So let's write this as work done by pseudo forces if non-inertial frame. If we are in an inertial frame, then there are no pseudo forces, this will be 0. This plus external forces plus all conservative forces and all non-conservative forces, okay, is responsible for the change in kinetic energy. Okay. Now, let's for a moment we assume that we are dealing with inertial frame of reference. Then we can say work done by external forces plus work done by conservative forces plus work done by non-conservative forces is equal to change in kinetic energy. Now let's take this work done by conservative forces to the other side. So work done by external forces plus work done by non-conservative forces is equal to change in kinetic energy minus WC. Now what is minus WC? We talked about that when we defined potential energy. That is change in potential energy. Okay, remember we define change in potential energy as negative of work done by conservative force. So then we have this equation, work done by external forces plus work done by non-conservative force is equal to change in kinetic energy plus change in potential energy. Only if a system has external forces, has no external forces and no conservative forces when a system has no external force and no non-conservative force, then WE is equal to 0 and WNC is equal to 0. So which leaves us with delta K plus delta U equals 0, which is nothing but kinetic energy and potential. So what is delta K? K final minus K initial plus U final minus U initial equals 0. If we keep K final plus U final on this side and K initial plus U initial on the other side, it means total kinetic energy plus potential energy is same for final state and initial state. Okay, so this is a very special case when, let's say, there is no external force, no friction, like no non-conservative force, only then this is valid. Okay, so work energy theorem and conservation of energy theorem is the same thing. So do remember, like this I would say is the mother of all equations. Okay, so remember, this is only valid when there is no external force, no non-conservative force, and also no non-inertial frame. Okay, now is the time to look at some of the problems. Okay, so let's say there is a spring. Okay, there is a mass attached to the spring. Mass is m. Okay, and after a while, due to gravity, the mass is at some distance x, it goes down, and the system is in equilibrium. Okay, find the potential energy due to the spring at equilibrium. Okay, so when it is at equilibrium, there is mg force acting here, there is spring force kx which is acting in the opposite direction. So because it is at equilibrium, then kx is equal to mg, or x we can say is mg by k. Now potential energy due to spring is half kx square, so you can write half k m square g square by k square, or this is half m square g square by k. Okay, next question. We have a semicircle. Okay, and there is a chain that rests on this semicircle like this. Okay, total mass of the chain is m, the radius of the semicircle is r. Okay, question is find the potential energy of the chain due to gravity. Okay, now because this chain is not on the ground, some part of it is above the ground, it will have some potential energy. And how do you find out? But just to look at something else, if the chain was on the ground, its potential energy will be 0. If it was, let's say, like this at a height h, then the entire mass is at height h. We can write potential energy is mgh. If the chain was like this vertically and the top part of the chain was, let's say, this total length is L, then the center of mass of the chain is at L by 2. So we can write mgL by 2 as the potential energy. But we cannot use any of the simple formulas here. This is a little complicated. We have to break this down. Okay? So let's see how we can do that. Okay. Let's imagine at an angle theta, okay, this point is at what height? So if I drop a perpendicular, so this height will be r sine theta. Correct? Now, if I take a small angle d theta, so that I have a small mass of this chain dm, which is at a height r sine theta, we can find the potential energy of this small mass dm, right? So we can write small potential energy du is equals to dm g times whatever this height is, let's say h, because it's like a point mass at height h. The potential of energy of that point mass, if it is m, is mgh. That's what we're doing here, dm gh. Okay. Now, can we find how much is dm? The total mass is m, so the linear density is m divided by 2 pi r will be the full circumference of the circle, but this is only quarter circle, so 2 pi r by 4, which is pi r by 2. So this is the linear density of the mass. But how much mass is there for this small theta angle is r d theta, right? So if you look at this curve, if this is theta, this is r, then this curve is r theta. So this radius is r, so that's r d theta. So r gets cancelled, 2m d theta by pi. Okay. So we can reduce this du as 2m by pi d theta g, and h is r sine theta. Or we can write this as, bring all the constants together, 2mr g by pi sine theta d theta. So that is the potential energy of this small mass du. Now, if I integrate both sides, integrate sine theta d theta, where theta ranges from 0 to pi by 2. Then that will give me, assuming 0 to u, let's say, that will give me the potential energy of the chain, assuming potential energy at ground is 0. Okay, so this is 2 mRg by pi, and this is minus cos theta integral, and ranging from 0 to pi by 2. Now minus cos theta, cos 90 is 0, so 0 minus cos 0 is 1, so plus 1, so this becomes 2 mRg by pi. This is a good problem. So let's say there is a hill, a rough hill, okay, and a body is here. A force acts on the body F such that it is always tangential to the surface of the body. A force F acts on the body such that it is always tangential to the surface of the rough hill. The coefficient of friction is given as K. Okay. Mass of this body is m. This height is h. And this length is L. Find work done by F from A to B on M from A to B. Assume F is applied very slowly. Also, F is variable. Okay, how do we solve this problem? Now, the key here is F is applied very slowly. When it's mentioned it's applied very slowly, it means there is no change in kinetic energy or no velocity applied. Okay, so let's use work energy theorem. Work energy theorem. Okay, what does work energy theorem say? Work done by all forces is equal to change in kinetic energy. Now, what are all the forces acting on this body? At any point, let's say at any point I take, and let's say the surface of the body was like this. We don't know how the surface of the body looks, right? At any point there is force due to gravity, there is a normal reaction which is tangential to the surface of the body, and then force of friction is tangential to the surface of the body, and F is also tangential to the surface of the hill, right? F is also tangential. So these are all the forces that are working on the body. Okay. Now, so work done by normal reaction plus work done by friction plus work done by this capital F plus work done by gravity must be equal to change in kinetic energy. And since the force is applied very slowly, gradually, change in kinetic energy is 0. Now work done by normal reaction, this is always perpendicular to the direction of motion or displacement, so this is 0. Okay. Now work done by friction we don't know. Work done by gravity we can also find out. Now gravity is a conservative force, so instead of taking a weird path we can also take a straight line path, or in fact we can just look at this height, because there is no work done by gravity when the body moves from here to here. Okay, only work done is when it gains height. So work done by gravity is mgh, but remember gravity force is downward, the displacement is upward, so this should be minus mgh. Okay, we will come to that, let's say. So our goal is to find out work done by F. So this is equal to, if we take this and this the other side, minus work done by friction plus work done by gravity. So work done by gravity we already know. The only problem then is to find work done by friction. Now this is interesting. Work done by friction is equal to friction force times dot product of the displacement, friction force and displacement. So let's zoom into this. Okay, let's say the curve is like this. Okay, let's say at some point on the hill work done by friction will be tangential and its magnitude would be mu times or k times normal reaction. Okay, normal reaction is perpendicular to the tangent. Mg is downward. Okay, let's suppose this angle is theta. Okay, when the body moves a small distance ds along the curve, okay, so this will be minus f, so small work done by friction, so minus fr times ds, small distance ds. Okay. Now Fr we said is k times normal reaction. How much is normal reaction? Is mg cos theta. So this is k mg cos theta. Okay, k mg cos theta. Now this ds, if I look at this ds, a small distance on the curve, okay, this makes an angle with the horizontal. How much would be that angle? This angle should be theta as well, because why? This is 90 degree, so this is 90 minus theta, so this should be theta. Okay, so this makes an angle theta. Let's draw ds a little bigger. This makes an angle theta. Let's drop a perpendicular from here to here. This distance is then ds cos theta, and this distance is ds sin theta. Now what is ds cos theta? We can also write this as dx and this as dy. If this is our x coordinate, this is our y coordinate. X direction, y direction. Dx is ds cos theta, dy is ds sin theta. Okay, so if we can replace this, minus Fr is k mg cos theta. Okay, and ds we replace by, so dx is equals to ds cos theta, or ds equals to dx by cos theta. Now cos theta gets cancelled out. This becomes minus kmg dx. So the total work done in moving from here to here is as if we integrate, because there is no y component here, right? We just, so total work done is 0 to L is the limit of x, k mg dx, or we can write minus k mg L. Okay, so we found work done by friction is minus k mg L. So then go back here. From here we can write work done by this variable force F is minus of work done by friction plus work done by gravity. So it is k mg L plus mg h. We can take mg common, kl plus h. Okay, so here we are applying work energy theorem, and it becomes easier to look at work done by the variable force F. Okay, this part is little bit involved, geometry, you'll have to look at that, but once you have figured this out, we can easily find out the work done by friction. Now gravity is a conservative force. This is conservative force. So we could do that find the work done by gravity in a different path very easily. But remember, friction is a non-conservative force. So it will be incorrect to just calculate friction along a different path, because it is dependent on the path. So that's the reason you have to integrate along the path. Okay? Cool. Okay. Let's say we have a force that is given as x I cap plus y j cap. Okay? Okay. Is F a conservative force? How do we find that out? So we can do the partial derivative del fx del y. So the condition of F being a conservative force is del fx del y should be equals to del y del fy del x, and del fy del x should be equal to del fy del z should be equals to del fz del y, and del fx del z should be equals to del fz del x. Okay, so these are partial derivatives. So we are differentiating fx with respect to y, treating x and z as constant. So what is del fx del y? So does x vary with y? No, 0. What is del fy del x? Does y vary with x? No, 0. So this condition is satisfied. Remaining conditions, del f del z is also 0. Fz is 0, so this is also satisfied. Del fx del z, there is no z here, so this is 0. Fz is 0, so this z is also 0. So all three conditions are satisfied. Then this is F is, we conclude F is conservative. Okay. If you have another question, F is given as y I cap plus z j cap plus x k cap. Is this force a conservative force? Well, let's find out. Del fx del y, how much is that? Fx del y is 1. Del fy del x, del fy z del x is 0. As soon as one of the conditions is not satisfied, this is not satisfied here, so therefore F is non-conservative. Okay. Now let's say this is the force given, and then the question asks that a body is taken from this point 0, 0 to A, and it goes to B, and it goes to C, so like this, and it then comes back to 0. Okay, this is the xy coordinate. Find out work done by F from in the journey, work done by F when moved from O to A to B to C back to O. How do you do that? One way to do it is you do F dot S in each part of the journey. So you have the force, you know how much displacement it is, let's say 2 comma or 0 comma 2, 0 comma 2, this is 2 comma 2, this is 2 comma 0. So you know exactly how much displacement is, you do dot product every time and figure out. But then we also found out that F is a conservative force. And we know work done by a conservative force in a closed path is 0. So directly you can find out the work done and mention it's 0. Okay? But if you were not aware the concept of conservative force, another student might just take the force and then do a dot product for each of these displacements and waste a whole lot of time and figure out that the work done was actually 0. Okay? And that concludes this episode. Hope it added some value to you and your concepts on work and energy is more or less clear now. I did omit a few things like equilibrium, which I will discuss in another video, and then I also missed out on defining what is power, but I will just include that in the other video as well, just so you are familiar with that concept too. So with that, let's close out this video.